In this video, I want to talk about autocorrelation and some of the consequences of autocorrelation. And we're specifically talking here about temporal autocorrelation. There's also spatial autocorrelation or other forms of autocorrelation. But here we're talking about having observations that are recorded over time. So we have the same variable on the same unit measured over different time points. And these observations are not independent of each other exactly because they are on the same unit. So you can, for example, imagine having a data set where we have the income per capita in Ireland and we measure this over time. So we have this for each year, say for 100 years. And we want to investigate this through some regression analysis, maybe link it to some other information we have over those 100 years. But the income per capita in 1 year is of course not independent of that of preceding years. Income per capita does not randomly vary between years. It gradually varies. So if the last year was high, this year is also going to be high. And so that leads to autocorrelation, to temporal autocorrelation, that the observation this year is not independent of that in preceding years. And in this part of the lecture, I will assume that we have just one unit that we observe over time. We will get to, when we get to panel data, we get to multiple units observed over multiple time periods. For example, a set of countries and measuring income per capita over several years. That would be a form of panel data, or in political science often called time series cross-section. But here we're talking about pure time series, so one unit observed over time. And because we do that, we also change the notation a little bit, and that is what this first few slides are about. So we have used the subscript I to indicate the unit. So we've talked about the data set of n observations, and then each time we talked about the ith observation. But now we're going to change the notation slightly. We're going to say that we have capital T observations, and we use the subscript small t to indicate an individual observation. So small t indicates the year, capital T indicates the number of years. So if I say y underscore t, it means the observation on the y variable for year t, or time period t, right? The theory is the same whether these are years or seconds or months or whatever. Secondly, an important concept is the idea of a lagged variable. So a lagged variable is a variable where we look at the previous observation. So often in an equation, when we want to say something about y at time t, we want to incorporate something about yt minus 1, exactly because it's related. So y underscore t minus 1 means the previous observation of y. And we can also do yt minus 2, yt minus 3, and so forth. That means 2 observations back, 3 observations back, and so forth. So when we talk about the lagged value on y or the lagged value on x, we are talking about a previous observation on the same variable for the same unit. The second thing that we sort of have to agree notationally is what we mean by this delta yt. So aside from the previous value on y or the previous value on x, we can also talk about the difference between the current value and the previous value. So we call this first differences. First differences are the difference between the current value on a variable and the lagged value on that same variable. So when I write delta y underscore t, I refer to the difference between y at time t and y at time t minus 1. And we can also think about lagged versions of that. If I write the first difference of yt minus 2, then I mean the difference between yt minus 2, so 2 values back, and t minus 3, so 3 values back. So it's still a first difference, but it's a first difference that was observed 2 time periods earlier. Yeah, and so in some textbooks they will talk about the difference between the current observation and 3 observations back. When I use this notation t delta y t minus 2, I mean the first difference observed 2 periods back, t minus 2 minus t minus 3. So when we have autocorrelation in the data, a number of problems occur. So similar to what we saw last time with heteroscedasticity, the point in the derivation of the estimator where where the autocorrelation comes in is when we make an assumption about the variance-covariance matrix of the errors. So there, in the normal derivation, when you run a normal OLS model, we assume that it is homoscedastic, that all the variances of the errors are the same across all observations, and has no autocorrelation, that off the diagonal they're all zeros. So we have this sigma squared times the identity matrix I, and then we can simplify the equation. When there is autocorrelation, these off-diagonal zeros are not zero anymore. And that means that we cannot replace. And that means that we cannot replace simply with sigma squared times I. And if you can't do that, then our calculation of the variance-covariance matrix of beta hat is incorrect. And this means we cannot trust our t-tests, we cannot trust our f-tests. And so that is quite problematic. We can still estimate beta, we have an unbiased estimate of beta, but we cannot trust the results. And we can also not assume consistency. Furthermore, we will probably overestimate our R squared, so we overestimate the fit of the model when we ignore the autocorrelation. And when the autocorrelation is positive, which is the more common pattern, there is such a thing as negative autocorrelation, that from year on year it goes radically up and radically down. But that's of course not so common. Much more common is that the data gradually changes from year on year. And in that case, the autocorrelation will be positive, and that means that we underestimate the variance-covariance matrix. That means that we underestimate the standard errors, and that means that we reject the null hypothesis too easily. So you will draw strong conclusions, you reject your null hypothesis that some effect isn't there. And those strong conclusions are based on incorrectly calculated standard errors due to the time series data. So that is all very problematic. There's one step further, and that is the problem of spurious regressions. So that I will explain in the next slide. So if we have two time series that are both non-stationary, and we will talk about non-stationarity in a separate video. But non-stationarity means that these variables, they randomly vary over time, gradually. So every value is an alteration on the previous value. It will go a little bit up, a little bit down. Think of prices of cars. Yeah, so prices of cars every year will go up and down a bit. And it will every year you can see as a change relative to previous years. But they are not stationary. Stationary means that over the long run there should be some average value. So you can think of the average long-term price of a particular car and think about how prices go up and down over a year. And there is no such long-term average, right? Because it's not the case that there is a true average price and sometimes we're higher, sometimes lower. It is just more like a random walk, the prices. They can always go up and always go down. There's usually inflation, they tend to always go up. So if there is no such long-term average, then we call this a non-stationary process. And if you have two non-stationary processes, so for example the average house price and the quality of the ozone layer or something. Yeah? So neither of those are stationary. They will change over time, but they're also unrelated to each other. They have nothing to do with each other. But because they are non-stationary, because they don't have this long-term average, if you would regress one on the other, so you would explain average house prices by the quality of the ozone layer in Ireland, you will find highly significant effects. You will get small standard errors, you can reject the null hypothesis, you will conclude that there is a strong correlation between the two, even if they have nothing to do with each other. And that is because when two time series are both not stationary and you relate them to each other, they will always show high correlation. So here, for example, is some randomly generated data. The blue line and the red line are both randomly generated. They have nothing to do with each other. So when I randomly generate, I don't look at the other variable. When I regress them, I find highly significant results. And that is what we call a spurious regression. Regressing two non-stationary time series onto each other will give you highly significant results without those variables being related to each other at all. And so we need to worry about this and we need to test this.